Hello everyone, my name is Kyoung-Hee Kim and I'm a professor of architecture at UNC Charlotte. Our topic is building level flood resilience. In this presentation, we will discuss how individual building design strategies reduce flooding risks, enhance the adaptability of buildings against flooding, and help their recovery from flood-related events. Increasing urban development and impervious surfaces are the major cause of flooding in cities. Streets, buildings, and subway systems are flooded and destroyed due to the lack of permeable surfaces. These frequent floods and destruction reveal the vulnerability of our built environments and underscore the urgent need for enhancing flood resilience. This slide presents a global map showing areas with increasing flooding risks. Overall, many regions across the globe are experiencing rising flooding exposure by 2030. Understanding predictions helps planning and implementing flood resilience worldwide. For example, South America, Southern Asia, and Sub-Saharan Africa in orange were susceptible to flood risks in the past and are expected to continue facing the risks in the future. North America and Europe, highlighted in pink, were historically experiencing fewer flood, but they are projected to face increased flood risks in the future. Nature integration offers multi-scale solutions to flood resilience on the building scale, the community scale, and the city scale. These nature-integrated strategies at different scales should systematically link and work together to help prevent overwhelming storm drains and lower the risk of flooding. While floods are widespread, the impacts are always felt locally on specific buildings and localities, especially in more socially and environmentally vulnerable communities. Green roofs, permeable pavements, and cisterns are building-level integration and can reduce stormwater runoff. Tree trenches, rain gardens, and sponge streets are effective strategies for community-level integration. These measures delay stormwater runoff while creating communal, occupiable green spaces after water has drained. Constructed wetlands, retention basins, and sponge city zones can reduce large-scale flooding across broader regions. Let's review the Resilient Design Framework: Original State, Mitigate, Adapt, and Recover. We discussed this framework in the introduction video. Original state represents the normal, stable condition of a building before disruption. For water resilient strategies, Mitigate involves proactive measures to reduce flood vulnerability onto and around the building and the site. At this stage, green roofs, permeable surfaces, and cisterns at the building and site levels can protect the building and site locally through soaking up and delaying water runoff. Adapt is the process of accommodating flood events. Sponge street systems, rain gardens, and flooding courtyards, etc., can retain stormwater so that the city's drainage and trenches are not overwhelmed. This increased lag time slows down peak flood levels and reduces overflow on rivers and infrastructure. After floodwater drains down, community-level measures safely store excess rainwater for community use. Rain gardens and flooding courtyards in public spaces temporarily store extended flooding and recover back to the original conditions once water dissipates. Finally, the last phase of release gradually discharges the collected water into the underground and replenishes groundwater aquifers. This recover phase stores and releases floodwater, greatly enhancing long-term water security. This flood resilience cycle enables the community to become more resilient to floods and return to its original safe and functional condition while conserving water resources. When it comes to flooding resilience framework, we need to think about scale and flood intensity. For moderate rain, solutions at the building and site level are often enough. At the building and site level, green roofs, biofacades, pervious pavements, and cisterns absorb stormwater, delay runoff, and store some amount of rainwater for building and site use. This slide summarizes the environmental and social benefits of green roofs. They provide multiple benefits, including stormwater management, building energy savings, biodiversity and habitat protection, urban heat islands effect mitigation, roof longevity, and aesthetics. Similar to green roofs, biofacades also provide a variety of environmental and social advantages. Let's quickly go through the benefits. They reduce air pollution, enhance building energy efficiency, and reduce urban temperatures. Next, they reduce sound transmission due to additional biomass and are effective in mitigating rainwater runoff, especially when soil-based biofacades are used. They contribute to biodiversity and urban ecology by growing numerous species such as essential pollinators, birds, and other ecosystems. Biofacades help increase productivity and creativity through providing the biophilic effect. Improving health and well-being is another major benefit because biofacades filter pollutants and release oxygen into the environment. This creates healthier built environments for users and the ecosystem. Performance metrics to evaluate the flood resilience can include stormwater runoff reduction represented by percent, peak flow delay represented by minutes or hours, and infiltration rate represented by millimeter per hour. These indicators help evaluate the effectiveness of flood resilience strategies. This slide shows a cross-section of different green roofs. An extensive green roof on the left is a lighter, shallower system with a thin layer of soil and hardy plants like sedums or grasses. It's relatively low maintenance and mainly focused on functions like absorbing rainwater and providing insulation. In contrast, an intensive green roof on the right is more like a full garden on a roof. It has deeper soil to support shrubs or even trees. It often is designed to be accessible for people to enjoy. Intensive roofs are heavier and costlier and require more maintenance because they're essentially parks or gardens. They can offer more biodiversity and recreational space. A semi-intensive green roof falls between extensive and intensive systems in terms of soil depth and vegetation size. This slide illustrates how different green roofs play a role in tempering microclimates around the building. The extensive roof on the left reflects the sunlight, which helps with solar gain. The center shows a semi-extensive green roof with a thin soil layer with low vegetation. Due to its biomass and soil mass, it reduces rooftop temperatures through shading and insulation. It also holds floodwater. The intensive green roof on the right incorporates deeper soil and supports trees or shrubs. The largest natural elements offer greater benefits, stronger evapotranspiration, more stormwater retention, and better indoor cooling. This type offers a tempering microclimate around the building. As we discussed in the previous slides, proper design ensures effective protection, delay, storage, and release of stormwater. This slide shows the construction components of a green roof. The system on the left uses planter modules, while the one on the right is a continuous green roof system. The green roof soaks up floodwater and channels it to cisterns, where it can be reused for the building or released to the site. Architects and engineers can choose different systems that best suit their project's goals, whether it's a lightweight system simply to manage water or a roof garden where deep soils are arranged for large green systems. Having these options means new or existing buildings can incorporate green roofs to help with stormwater management, urban ecology, and social binding. This diagram illustrates different cisterns, floodwater storage both above ground and underground. Rainwater from rooftops and building surfaces is stored in tanks for later use, such as irrigation, non-potable building demands, or release to aquifer. Cisterns on the ground level are often more accessible for maintenance and retrofitting. Alternatively, the cistern on the right is an underground water storage system. This method saves space, provides large volume retention, and enhances site aesthetics. Across these systems, from green roof controlled water channels, and cisterns enable effective delay, storage, and release of rainwater, contributing to resilient water management. This precedent shows a tiled green roof typology where vegetation on the slope plane can receive better solar exposures while improving visibility appeal of the green roof. The design makes the green roof more interactive by integrating a public gathering space surrounded by the tilted landscape. The tilted angles can be optimized for water drainage toward water collection zones, supporting stormwater management while contributing to urban ecology and cooling. This precedent illustrates a terraced green roof covering a vast area. It is one of the largest green roofs in Asia, located at Thammasat University. This terraced green roof marries traditional farming practices with modern green technology. The green roof is well blended with pedestrian ramps and stairways, providing multifunctional recreational space and ecological zone. The terraced green roof helps slow, store, and gradually release excessive water to the site, reducing flooding risks while recharging groundwater. This extensive landscape roof area contributes to restoring urban ecology and cooling down the surrounding temperature. The case study focuses on the undulated green roof located in the Leeds Skelton Lake Services facility. The undulating wave-like geometry mimics natural landscapes and site design that is like surrounding context. The soil profile of the roof and varied elevation promote natural drainage and divert water to designated water channels and collection points. The green roof's dip and peak, aligned with the interior space naturally, form gaps that create clerestory windows for daylight illumination. The clerestory window minimizes electric lighting load and provides a bright indoor environment. This project demonstrates a balance between the architectural form with its ecological performance, aesthetics, and user experience. This slide illustrates a scalloping green roof typology characterized by its clearly dividing planter zones and public space. Each planted area is tall and framed with a strong visual and functional separation. The sculpted planting zones offer controlled environments for diverse vegetation types ranging from grass and shrubs to edible species. The remaining zone is designated for public access and unobstructed walkways for users. The scalloping planter areas further enhance effective stormwater mitigation and absorb rainwater for slow release. This typology offers organized spatial uses and urban ecology. This video was supported by UNC Charlotte in collaboration with the US-ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. Let's continue to innovate for a resilient future.